Hi everyone, my name is Combriat and I'm working on the Abino project and I'm part of the physics department. And today I will try to talk a bit about acoustics and biology in the Abino project. So to start simple, what is acoustics? So acoustics is basically the study of sound waves. And what is a sound wave? A sound wave is just a local change of pressure in time that does propagate in a medium. So to take an example, for instance, if you have a loudspeaker producing some music or some sound, this loudspeaker will actually produce a pressure wave which will leave from the loudspeaker toward a target, for instance, your ear or a microphone. As we can see on this animation, so this pressure is oscillating up and down, and that's what does carry the sound. And we also see that it needs a medium in order to propagate, so it doesn't propagate in vacuum, but sound waves do propagate in air. That's what we usually use in order to talk, but also in liquids or in solids. What is interesting is that if we zoom on this medium and we look at what is actually going down at the molecular level of, for instance, the air of the liquid in which a sound wave is propagating, we can see that actually the sound will make the molecules or particles composing the medium oscillate. So on this animation, which is basically the same as the previous one, I just added the molecule constituting the air, for instance. And you can see that actually at the top part of the wave you have more particles because the pressure is higher, and that's basically the definition of pressure. But you can also see that even though it seems that all this high density bunch of particles are propagating alongside with the wave, actually they are just oscillating around an equilibrium position. So in order to see that more clearly, you can focus on the black particle, which is in the middle of the screen, which is just different by its color. And you can see that it's actually oscillating back and forth, so that a sound wave is not propagating any matter. No matter gets displaced, they are just oscillating back and forth. So why is that interesting in terms of the Abino project? So now we can think in terms of biology. So if we input a sound wave, for instance, inside a body, or if a body is subjected to acoustic waves, this will actually make the component of the biological material, so cells, oscillate back and forth like this. And that will be principally the biggest effect on the principal effect that you can expect when inputting sound wave inside biology. Other things can also happen which are basically consequences of these oscillations. So when you input a sound wave inside a body, you can also expect some heating, for instance, of the cell. And that's actually used in medicine in order to remove tumors or cancer cells by just ablating them using heat to make them die. Other thing that can happen is that you can create bubbles when you put too much intensity of the sound. And that's actually what is happening, for instance, when in decompression sickness, where you have bubbles just popping out in your bloodstream, and that can be very dangerous, for instance, when these bubbles are blocking bloodstreams, for instance. Another effect is that acoustic wave can bounce, and that's happening all the time when you are speaking on walls and things like that. But in the human body, they can also bounce on different kinds of tissue, for instance, on bones and on organs. And that's actually the principle which is used in ultrasound imaging. And there are a lot of other effects that I won't talk about today. So just to sum up, acoustics is just a way for us to input some mechanical energy inside a biological material. So, as I already told you, acoustic waves and acoustics are used on a daily basis in hospitals in order to do, for instance, ultrasound imaging, which is kind of diagnostics, but also in order to cure people, for instance, to remove deadly cells such as tumor or cancer cells. on a more fundamental point of view, it is known in biology that cells do react to mechanical stimuli, which in a process called mechanosensing. It means that, for instance, if you probe a cell with a mechanical signal, if you push it, if you stretch it, if you compress it, then the cell will react and that can trigger some biological change at the cell level. So the main question I'm trying to address in this project is it possible to influence a cell behavior using acoustics as a mechanical stimuli? So just to follow up on what Chen just talked about, stem cells that we are now able to produce from whatever cell from your body can become any type of cells. And in particular, in the Abino project, our goal is to try to make stem cell into beta cells which are producing insulin. And the way this is usually done is to use drugs and chemicals in order to influence the cell differentiation in order to go toward the insulin producing cell. But there are also new trends in biology trying to use other kind of stimuli, such as mechanical stimuli, in order to help or even to trigger this differentiation process. And that's why we are just trying to use acoustics in order to help stem cells to differentiate into insulin beta producing cells. So just to finish about what we are actually doing in the lab, and so what is my work on an everyday basis. So it's not clear for us as physicists to understand what is actually the effects of ultrasounds on cells, on biological material. So it has been claimed for years in ultrasound imaging that it's completely doesn't have any effects, or bad or good effects. On the other hand, some people are using that in order to cure or to remove cells. So we know that something at some point should happen. So in order to understand what is happening at the biological level when using acoustics, we are, for instance, doing experiments where we can monitor cells undergoing acoustics signals. So, for instance, on the movie here, you can see a bunch of cancer cells actually undergoing an acoustic excitation. And if you focus on the two in the middle, you can see that they are actually undergoing an oscillation because of the acoustic wave. We can actually see that they are kind of dancing in the acoustic field. And so that's the first part as a physicist to understand what is going on, is just to monitor actually what are the direct effects, so the physical effects. And the second part in my job is to try to understand what these stimuli are actually doing at the biological level, so just trying to get a biological output out of this. So, as a physicist, we like to reduce things to a very small set of parameters. And for instance, we are now wondering what are the important parameters in the sound wave that can influence the cell behavior. And there are a few that you can think of straight out of the box. So for instance, one can think about the intensity. So here you have a loud sound, whereas here you have a very silent sound, which is that we can call the volume, basically, of the wave, if you speak in terms of music. Another thing that we can think of is what we call the frequency, or that musician calls the pitch. So you can have a treble, for instance, kind of sound, like this, or you can have a bass sound, like this. And that is another parameter that can or not change actually what is going on at the cell level. And the last one that we can think of, but I'm letting the next speaker talk about a bit more about that, is what we call the repetition rate. So basically, is the sound continuous, or is it segmented, or does it have a kind of a patterning? Like this. So basically, my whole job in the Abino project is to broadcast music to cells in order to see if they actually react or not to this. Thank you very much.